Rigaku is tinfei, or TMA, specifically for the thin film. So not only can it be used for thin films, but there's also foils, wires, fabrics, anything that is within the 10 to 200 micron range. So for specifically for thin films, we can go all the way down to negative 150, which is good for, TGs of fluorinated polymers, all the way up to 600 degrees Celsius. Its primary use is for, polymeric thin films. So high temp of 600 is more than plenty. And then because it is a thin film, we're going to need to apply a little bit of a load to keep it from sagging or buckling during the measurement. So we can apply a tensile load as low as 1 millinewton, or we can go as high as 1,000 millinewton. And lastly, for the film dimension, as I mentioned, anywhere between 10 to 200 micron is good. After that, we'll have to switch to regular TMA. The film length, there's three options. We can either have 10, 15, or 20 millimeters in terms of length. And then our width is going to be limited or fixed at 5 millimeter. One really interesting thing about the Rigaku TMA is that it does have the option for a humidity generator. So this goes beyond the standard ideal condition. And now we're bringing it out into the real world application. We can add humidity. So our inlet stream to the instrument can have anywhere from room temperature to 85 degrees Celsius in terms of temperature. And then from that, our RH, our relative humidity, can span from 5 to 90%. So what this does is we can now determine how much it'll shrink or grow whenever we take away or add water. So the coefficient of hygroscopic expansion. Now, this is pretty useful for things such as fabrics and hygroscopic thin films, but we've also seen an interest in metallic foils under humidity as well. So this is what your standard TMA thin film graph is going to look like. This example is thin film polyether ether ketone, or PEEK, as we show here. We see there's two primary regions. The first region on the left side of the graph is going to be the glassy zone, or the vitreous zone. Then as we increase, the expansion will curve to a new zone. That is the rubbery zone. And then if we take the tangent of each of these zones, we combine them and we'll get a pinpoint location. That is where the glass transition point occurs. So PEEK, for example, is very chemically resistant. It has high mechanical strength, especially at high temperatures. So an example of its use would be the flexible printed circuit boards in electronics.